This is Lab 2, Projectile Motion. Purpose of this lab is to investigate the motion of an object that is thrown like a projectile. This will be done using experimental data and two computer models. The main fundamental physical principle would be the momentum principle. As a preview, it was shown that projectile motion is parabolic and drag slightly warps this parabola, and that the computer model with non-zero drag coefficient was more accurate than the computer model without drag. So the main model to be discussed is the momentum principle, which states that the net force is equal to the change in momentum over the change in time. And so using this, you can obtain the velocity update formula and then extrapolate that to the position update formula. The only thing they had to consider is the net force, which is equal to drag plus the force of gravity, which are calculated using these two equations here. The reason that we're using this is because net force is not constant. That's why we have the V final here instead of V average. And it's also because the motion in the x direction is independent of the motion in the y direction. Our main assumptions are the force of gravity and drag are the only forces acting on the object, and the force of gravity is actually constant. For the method, we're throwing a ball at a slight angle and recording its motion, but then only cutting it so that it starts at the highest point. And then you just take the data from Tracker and paste it into Excel sheet and compare it with computer simulations. And so using this method, the system is a scrunched up paper ball. The surroundings is the earth that exerts the force of gravity, air that exerts the drag force, and then these initial positions are all just obtained from the video. It was thrown from an initial height of 1.6 meters. The velocity was exclusively in the x direction, and the mass of the sheet of paper is 0.005 kilograms. So this is a video of what the experiment looked like. All right, so using these numbers, you can set up the code. So first you initialize all these variables using the initial conditions. This should say 1.6 meters, but that's accurate here. So initialize the position, velocity, the mass, as well as the change in time, which is 1/30 seconds. And then after that, inside the while loop, you're defining drag, you're defining the force of gravity, and saying that the net force is equal to the drag plus the force of gravity. So using the net force at that instant, you update the velocity and then update the position. And then after that, you advance the clock and do it over again. So what this shows is that for non-zero drag, you have position in the x direction is a perfectly linear function of time. In the y direction, it's a quadratic function of time sloping downwards. The velocity in x is constant, and the velocity in y is linearly decreasing, and it gives us parabolic trajectory as shown in these two. With non-zero drag, it's very closely the same thing, but it's slightly, like the parabola is slightly moved, like squished inwards because drag resists motion. So the x position is not perfectly linear. It's like the slope of the velocity is negative, so it's decreasing. And for the y, it's actually increasing slightly because drag force is opposing the downwards motion. Overall, what this shows is that with no drag, x positioning its time should be perfectly linear, but with drag and in real life, it becomes slightly lower. For the y position, it's the same thing. The code with no drag is a perfect parabola, but it becomes slightly warped with drag. And lastly, for position against for x against y, it's a perfect parabola without drag, but becomes slightly squished inwards with drag, as shown by the code with drag in the experimental data. However, there were some sources of error. The main one is human error when using Tracker. That's because it was difficult to pinpoint the exact center of the paper ball. This is like the main source of error. The trajectory of the ball might not have also been exclusively in the XY plane. The equation for the drag might not have been entirely accurate since the scrunched up paper ball wasn't an ideally like point object. And that there were other forces in effect such as wind or a slight breeze, as well as the Magnus effects, which happens if the paper ball was rotating. What's interesting to note is that none of these showed terminal velocity because the velocity versus time never became constant. You kind of see this level out near the end. But to find terminal velocity, you could simply just extend the time in free fall, so maybe throw from a greater height, or just use a different lighter object such as a feather. And lastly, if you were to throw it straight up, then the initial velocity becomes non-zero in the y direction, meaning it would take longer to reach the ground. So this is essentially just the position update, just the kinematic equation for constant force, And if you plug in different values for the initial velocity in the y direction, it's shown that if you were to throw it straight up, then the time would be greater than if you didn't. Even though this assumes the net force is constant, the general idea will still apply because drag opposes motion. So in conclusion, this shows the projectile motion is parabolic. X position is a linear function of time, but y position is a quadratic function of time, and that drag opposes the motion. And that the computer model with drag closely matches the experimental data.